Hi guys, this is topic 55. This is logistic differential equations part 2. This is going to get a little more advanced than part 1, but this is probably a little bit harder than what you'll see on your AP exam, but just in case you happen to see this on your AP exam, we're going to go over this as well. And it's a good review of what we did in topic 54. So the rate, which again means derivative, at which the fluid spreads through a community is modeled by the logistic differential equation dp dt is equal to 0.001 p and then 3000 minus p. So first thing you should be thinking to yourself is, where is the carrying capacity? Nice thing about this one, it's already factored for you. So the carrying capacity is going to be when this factor 3000 minus p is equal to 0, which is obviously when p is equal to 3000. So my carrying capacity is P is equal to 3000. And then I know that all my logistic differential equations look similar. In this case, my initial conditions, P at 0 is equal to 50. So I'm starting here at 50. And then it's going to go up and reach 3000 right there. So this part would be 50. This would be 3000 up here. So again, my rate of maximum growth, or the point where I have a point of inflection, or the point where it goes from increasing at an increasing rate to increasing at a decreasing rate, is always half the carrying capacity, no matter what my initial condition is. So this point here would be at 1500, since that's half of 3000. Okay. So that's kind of the stuff we did on last topic 54. And then what's going to make this one a little bit harder is now we're actually going to solve this logistic differential equation. So given my initial condition here, solve for p as a function of time, and all work must be shown. So this is going to take a little bit of room too. So this is a differential equation, so I obviously start off by separating variables, right? So I get dp is equal to, and just like we did before, we're going to take this dt and move it up here. So I get 0.001 p, and then 3000 minus p, and then dt goes up there. And that means that p terms need to go over here with the dp, and t terms need to go over here with the t. Well, there are no t terms, but I have these two p terms that are factored out that need to go over here. So they're on top over here, so I divide them to get rid of them, and that's going to move them to the bottom over here. So I would have 1 over 0.001 p, and then we're going to just separate that out and do 1 over 3000 minus p dp is equal to, and then just over here, you're just going to have dt. Now, really, I could put this over just one fraction, or put 1 over all of this. So it's 0.001 p, and I'm going to go and put parentheses around that, and then 3000 minus p around that, dp is equal to dt. Okay, so my variables were already separated. I just took these two things and wrote them as one thing. So variables are separated. Second step is to integrate each side. The right side's the easy one. The left side's the one that's difficult. Let me go ahead and scroll down a little bit. All right, so how do I integrate this mess? Well, guess what? I have two things that are factored out. So like we did in topic 46, we're going to do this by partial fractions. So I'm going to do a over 0.001 p, and then plus b over 3000 minus p, and that's going to be equal to the top, which in this case is 1. We'll crisscross them, so I get a times 3000 minus p, and then plus b times 0.001, which is 1,000ths, and that's actually probably a little bit easier to do it in that fraction form. So I'm going to do 1 over 1,000 p, and that's going to equal 1. All right, like I did before, I'm going to let p in this case equal, to get rid of this one, we're going to make p equal to 3000. So that whole term will go away. 3000 divided by 1000 gives you 3. So you get 3b is equal to 1, which means b is equal to 1/3. And then let p equal, give you a chance to think about what you want to make p over here to make this one go away. Well, be careful, it's not 1,000 because 1,000 divided by 1,000 would be 1. So you're going to have to let p equal 0 because 0 times anything is 0. So that'll give you 0 over there. When I plug in 0 for p here, that's going to give you 3,000. A is equal to 1. So A is 1 over 3,000. So not an exactly nice number to work with, but that's what we end up having. Okay. So the A, which is 1 over 3,000, goes with this one. So I'm going to put that 1 over 3,000 out front, and then I'm going to integrate. Let's go ahead and write this as 1 over 1,000, which I can pull out front, and then the P is going to, actually it's going to be 1 over 1,000 on the bottom, which will flip to 1,000 on the top, which I can pull out here. So let's go ahead and make that 1,000 on the top. The zeros will cancel, so that's going to end up being 1/3. And the P is still on the bottom, so this becomes 1 over P dP. And then separately, plus B is 1/3. Again, I'm going to pull that out front. And then I have the integral of 1 over 3,000 minus P dP, and equals the integral of dt on the other side. So now I've done up all the prep work. In this case, I'm integration by partial fractions so that I can integrate this mess over here. So 1 over p, this is just p, so I don't need u substitution. It just becomes ln absolute value of p. And then plus, this will be 1/3. And then this one does require u substitution since it's not just 1 over p. So I make u equal to 3,000 minus p. The derivative du would be -1 dp. So I'd have to put a negative here, which means a negative out front, which means I need to erase this and make that a minus sign. Then it's 1 over u, which is ln absolute value of u, and replace u back with 3,000 minus p. Equals the integral of 1 dt is just t. And then plus c. And then I use my initial condition to find c. I already forgot what my initial condition is, so let's go up here. P at 0 is equal to 50 is my initial condition. So I'm going to go and write that here. So what do I plug in for t in this case is the 0, and what do I plug in for p is the 50. Let's go ahead and condense this down. So I can factor out the 1/3. Using my log rules, I can write these two ln's as 1 ln, and then this will be absolute value of p on the top, and then minus becomes division of 3,000 minus p on the bottom. And then again, t is going to be 0, so that's just going to be my c value. I need to plug in 50 here, so that gives me 50 over 2950. And then 1/3 ln of that is equal to my c value. I guess if you want to reduce that down, you can make c equal to 1/3 ln. That 0 cancel that 0. These are both divisible by 5. So let's see, that would be 1 over 59, I guess. So not a very nice thing to do. And you can see why. They usually don't ask this on the AP exam because it takes some time to do. So now I'd have to take that, plug it back in up here. So I have 1/3 ln absolute value of p minus 1/3 ln absolute value of 3,000 minus p equals t plus 1/3 ln of 1 over 59. So yeah, yucky numbers. All right, so how do I solve for all this mess? So first thing I should notice is this term doesn't have a ln, but the other ones do, right? So let's go ahead and multiply everything by 3 just to get rid of this 1/3. So that'll be gone, that'll be gone, that'll be gone, and this will become 3t. And then I'm going to condense this down to 1 ln, so that'll be ln of p over 3,000 minus p equals 3t plus ln of 1 over 59. And I'm solving for p here, which makes it even less fun. So I'm going to take raised to base e to get rid of ln. So I get P over 3000 minus P equals, this has an ln and plus will become times, so it'll be 1 over 59 e to the 3t power. And then it gets even messier from there. So I guess I should pull up probably a blank piece of paper for you. All right, let me go back to where I was at. So I have P over 3000 minus P equals 1 over 59 e to the 3t power. Going to get rid of the fraction first, so multiply each side by 1000 minus P, or 3000 minus P to get rid of that. Now I'm going to have to take this and distribute it to both of those, so I get P is equal to 1 over, or actually 3000 over 59 e to the 3t minus 1 over 59 e to the 3t times P. Then I got the P terms on the same side, so I got P, that'll become plus 1 over 59 e to the 3t P equals 3000 over 59 e to the 3t. Then I can factor out a P, and that gives me 1 plus 1 over 59 e to the 3t equals, the side will stay the same. And then I can divide that away, and that gives me P as a function of time is equal to, let's go ahead and write it this way, 3000 e to the 3t over 59 times 1 plus 1 over 59 e to the 3t. And in this case, I'm actually distribute that 59, so that gives me 3000 e to the 3t power over 59 plus e to the 3t power. And that's my P of t. So again, not very fun. And don't you dare try and cancel out those e to the 3t's, because this e to the 3t is added to that. So that's my original function. Again, stuff that we've done before, not very simple to do, but it involves a lot of good review stuff. And I'm sorry about this getting kind of slanted here, but that's what happens when you try and draw on this particular pad. All right, let's go back to the actual problem now, because that was only part A. And right about now, you're probably thinking, why didn't I sign up for AB instead of BC? But this is usually a pretty easy problem on the AP exam. It's usually not this hard, but just in case. Okay. All right, I'm going to use that solution to A and my graphing calculator to find the size of the population when t is equal to 2 days. So that's just plug it in 2, so that's not too bad. And then we're going to use my graphing calculator to find the number of days that have passed when 2,400 people have contracted the flu. So let me go back to that blank paper that I was on. Okay. So first part's easy. That's just, so for part B, I'm just plugging in P at 2. Okay. And I'll go ahead and pause a second and plug that in my calculator and get you the answer. All right, once I plug in 3000 e to the 6th power and then over 59 plus e to the 6th power, at 2 days I have 2,617 people, if I round to the nearest person. And then for part C, I was finding how many days had gone by when I had 2,400 people. That would be graphing this. So let me go ahead and pull up the graphing calculator so you can see what I'm plugging in just for review. Let's see. There we go. Pull this over here so you can see it. I already had something in there, so go ahead and cheat and clear everything out of there. All right, so in Y1, I'm going to pull up my fraction bar. And put in 3,000, whoops. e to the 3x power. Oops, didn't want that. All right, and then on the bottom, 59 plus e to the 3x power. That's not e. All right, and then in y2, I'm going to put 2400. I've changed my window from day 0 to day, well, 2600. We're at day 2, so let's go to day 3. And then for y-min, just start at my carrying capacity, or my initial condition of 50, and go to my carrying capacity, which was 3000. Okay. All right, and graph that. So this is my logistic differential equation. And it's kind of nice to see the graph on the calculator as well of what my logistic differential equation looks like. And it looks like I did it right because it's reaching that carrying capacity perfectly. There's a 2400 coming across. So second calc, number 5 for intersection, enter, enter, enter. And that gives me a time of, looks like 1.821 days. So kind of cool to see the result of all that hard work that I had to do to get the original function, that it actually looks like your logistic graph. So again, I'm starting at 50. My carrying capacity was 3,000. It's going to be increasing at an increasing rate until half the carrying capacity of 1,500, and then it'll start to increase at a decreasing rate as well. So as far as the answer goes, it was 1.821 days. So for part C, P at 1.821 days was equal to 2,400. And this would be in people, just like this was in people as well. All right, so again, not an easy free response question, but it is something that they could potentially ask, because all that's on the course syllabus for this class. Oops. All right, let's go to an example of a free response question. This is probably more what I would expect to see on your test, is a question like this. So this actually starts off as just a regular differential equation, and then it switches to being a logistic differential equation. So you should probably be asking yourself, well, first of all, let's go ahead and read it. In a national park, the population of a mountain lion grows over time at t is equal to 0, where t is measured in years. The population is found to be 20 mountain lions. That and that put together are my initial conditions. Okay. So t of 0 is equal to 20. So one zoologist suggests a population model P satisfies the differential equation dp dt is equal to 1/4 parentheses 200 minus p. So now I know this is just a regular differential equation because there's just one p. There's not a p outside factored out and a p inside the other factor like you have down here. This one down here is a logistic differential equation, because again, if I distributed this, I'd have a q term, and then I'd also have a q squared term as well. Luckily for both of these, they already factored out for us. And they were nice, and they gave me a hint: use separation of variables to solve this differential equation. So this is just your standard AB one that you might see on your AB test. So move the dt up, you get dp is equal to 1/4 parentheses 220 minus p dt. And that means the p term needs to go over here with the dp, and any t terms need to go over here, but I don't have any ones, t terms. So the 1/4 does not have to go with the p term. The 200 minus does have to go with it, so I'm going to leave the 1/4 over there. So when I move it over here, it goes to the bottom is 1/200 minus p dp is equal to 1/4 dt, and I've now separated my variables. Second step is to integrate each side. I am going to have to do u substitution here, so make u equal to 200 minus p. The derivative is negative dp, so I have to put a negative there and a negative out front. And then it's going to become 1 over u du is equal to integral of 1/4 dt. If you want to move the 1/4 out in front of the integral, that's okay too. So the integral of 1 over u is ln absolute value of u. So you end up with negative ln absolute value of 200 minus p. Integral of 1/4 dt would be 1/4 t. Always put the plus c on that side like before. And then use my initial condition to solve for c. So p is 20, so that's going to be negative ln of 200 minus 20 is 180, and I don't need the absolute values anymore. T is 0, so c is negative ln 180. Okay, go back up to that step. So negative ln absolute value of 200 minus p equals 1/4 t minus ln of 180. And then I'm solving for p, so the first thing I'm going to do is get rid of this negative, so that changes the sign, so it'll be positive ln 200 minus p equals, this will become negative 1/4 t, and this will become plus ln 180. And then to get rid of ln, I raise to base e. This term doesn't have a ln on it, so that'll be the one raised to e, so it'll be absolute value of 200 minus p equals, let's go ahead and do this one first because e to the ln 80 or 180 is just 180, and plus is going to become times. So that's 180 e to the negative 1/4 t power. And then let's go up here. When I drop the absolute values, that other side becomes plus or minus. So 200 minus p equals plus or minus 180 e to the negative 1/4 t power. And then you subtract 200 to get rid of that, and that gives you negative p. So I'm going to change the sign. So p as a function of time is going to be plus or minus 180 e to the negative 1/4 t plus 200. And then when I plug in my initial condition of time 0, I need to get out 20. Well, obviously negative 180 plus 200 is going to give me the 20, so it's the negative answer. So p as a function of time is going to be negative 180 e to the negative 1/4 t power plus 200. And that's my answer to part A. All right, for part B, a second zoologist suggests a population model that satisfies, sorry, this kind of got cut off, but this should say dq, and this should be 1 over 500. So it's already factored for you. You should be able to look at this and tell me the carrying capacity is what? And hopefully you know that's 220. It wants to find the value of dq dt at the time when q grows most rapidly. So you might be afraid that you're going to have to do the same thing we did in part A with this, but since you know that growth occurs most rapidly at half the carrying capacity, well, half of 220 is 110, so that's going to be your answer. So B is going to be find the time, so that's going to be at a Q of 220, and I'm finding the value of dq dt, so dq dt is going to be the 110, sorry, not 220. So dq dt grows most rapidly when q is equal to 110, which is half the carrying capacity. And then to actually answer this question, I'm finding the value of dq dt, so I just got to plug in that 110. So dq dt max equals 1 over 500, and then 110, and then times, because I'm replacing this q with 110 and this q with 110, and then 220 minus 110. And I would not try and do that math, just circle that as your final answer there. So one of the things I can throw on a differential equation problem where you separate variables is they can, on the BC test, they can change it to a logistic growth. If you see this in free response, that's what I expect, is one part of a total free response question that has to do with the logistic growth. What I really expect on your test is one multiple choice question, and it probably won't show up in free response, but if it does, it's probably just going to be part of a free response question. Okay. All right, for part C, this is also good review. For the population model Q introduced in part B, use Euler or Euler's method starting at t is equal to 0 with 2 steps of equal size to approximate Q at 10. So this is a good review of Euler's or Euler's method. That's the one where you make the table. So remember, it's x, y. In this case, it's going to be t and q. And then my differential equation dq dt, and then dq is equal to dq dt times delta t. Starting at time 0 with my initial condition q of 20, I'm going up in 2 steps of equal size to 10, so this is going to be 5 and this is going to be 10. So remember, on Euler's method, you can always do that particular part of it as well. All right, so now on my differential equation, let me go ahead and write it down here. So the differential equation was dq dt is equal to 1 over 500 q, and then parentheses, make sure that's right before we go on, 220 minus q. All right, so I take my t is 0, which I don't have any t's, and q is 20, and plug them in. So 220 minus 20 is 200. 200 divided by 500 is just 2/5, and then 2/5 times 20 will be 40 times, or 40 over 5, which is 8. So dq dt at that point is going to be 8. And then dq dt is going to be 8 times my delta t is going up by 5, which gives me dq is 40. Remember, that's my change in q, which I add to this. So this would be 20 plus 40, which equals 60. I kind of skipped showing the math here, but remember, you should show the math here like I did on this one and I did on this one. Okay. So now I'm going to find dq dt with those numbers. So dq dt at t is equal to 5 is going to be 1 over 500. Replace q with 60 now, and then 220 minus 60. And this was a non-calculator problem, so you'd have to do this in your head. So this is going to be 60 times 220 minus 60 is 160, and then 1 over 500. Well, this 0 on top will cancel that 0. This 0 will cancel that 0. And 6 times 16 is 96 over 5. So that's 96 over 5. Oops, sorry, not there. 96 over 5 goes right there. And this math looks like it's going to be not very nice, but again, they usually set it up so that it's nice. So it's going to be 96.5 is my dq dt times my delta t is 5, and you can see the 5's cancel, so that gives you 96. So this would be 60 plus 96, which is 156. That's where my answer is, because remember, these last two ones will always be 0. So again, in free response, write it out. Q of 10, Euler's method is one of my 4 approximations, is approximately 156, and then box that as your answer. Okay. So good review of Euler's, or sorry, Euler's method as well. Okay. All right, as far as your assignment goes for this one, number 1 is kind of like we did in 54. Problem number 2 on the front is the harder one, like I did here, where you have to take a logistic differential equation and solve it, like I did on this piece of paper here and on the next piece of paper. So there's definitely not enough room on your assignment, so make sure you write this out on a separate piece of paper. So there's only one of these problems, but it's a good review of partial fractions and separating variables and all that good stuff. So see how you can do on number 2. It's definitely the hard one. And then the back side is just some multiple choice questions from previous AP exams that hopefully are pretty easy. And again, once you get done, scan this, take a picture of it, email or text it to me so I can look to see how you guys are doing on this stuff. These are the only two topics on logistic differential equations. So after this, we'll be moving on to probably parametric equations next, which is going to involve some memorization. Then we'll go to polar, and then we'll go to series. And boy, it sure would be nice if we're back in school by the time we got to series, but we'll just see how everything goes.